Section 2, objectives. What do we want to accomplish in this one? Remember we talked about those 4 different ways that we can calculate. We can go from moles to moles, or grams to moles, or moles to grams, or the whole thing from western Omaha to eastern Council Bluffs, the grams to grams one. Okay, so we can calculate the amount of moles in a reactant or a product from the amount of moles, so that's a mole to mole problem. The next one is calculate the mass from an amount of moles that's been given. So this is the moles of known to mass of unknown. The third one is calculate the moles of a reactant from the mass of a reactant or a product. So this is one which would be going from grams to moles. And then the last one is, if you start out, if they gave you the mass of a reactant or a product, you have to do the unknown one in mass. So it's just the 4 kinds of problems is what we're going to practice in here. Some of you could probably already do it because you have all the tools already to do it. So it's just to go over it, to make sure that you got it down. So in reaction stoichiometry, the calculations described in this chapter are all going to be theoretical, what that means is I may not get as much as it actually predicts, because in the real world, things don't always turn out exactly as you'd expect, right? In theory, if I burn gasoline in my car, I should be able to get all the energy in the gasoline to make me go down the road. That doesn't turn out to be the case. Like on your car, even the best cars, I think, are only like 40% efficient. The ones that get the really high mileage, they're only 40% efficient. We're wasting 60% of the gasoline. So that's kind of this idea here. So what this does is it just tells us the amount of reactants and products in ideal conditions. And then quite often, if you have somebody working as a chemist, maybe their job is to try to figure out how can I improve the conditions to increase my percentages that I'm actually getting. I had one of my former students who was a chemist, but he worked for a food company. It's Williams Foods. I don't know if they were just in Kansas City or not. I know that Walmart carries it, and I've seen it up here, but when they made a food product, one of his jobs is to make sure that what was marketed, what you bought in your container, actually is what it's advertised on there. So you can use chemistry in that way. You don't have to do, necessarily working in the petroleum industry and doing all those things like that. There are many uses for chemistry. I just don't have, I can't point back to a lot of students that I have that, went on in chemistry. Just not, I guess I didn't aspire too many of them to go on in chemistry. I have 2 of my students that have their PhDs in chemistry, so I didn't ruin them, I guess. And then this boy, or this guy, he's not a boy anymore. He's, I think he even has grandkids already. So, I have some of them that are chemists, but not all that many. I have a lot more that are engineers probably than chemists. Now, many of these reactions, it says, don't proceed such that all the reactants are completely converted into products. That is one of the things that some of you will run into in the combination of chemicals that you're going to pick to make your 2 grams that I keep referring to. Some of you are going to run into this issue that not all of the reactants will be converted into products. In theory, it should be 2 grams, but maybe in real life it doesn't come out to quite 2 grams. So, and like for instance, most of these things that you're going to be making are going to be precipitates. Maybe not everything precipitates. Maybe some of the precipitate is still soluble in water, so you only get part of it. So all these different things that can keep us from getting the theoretical amount. So the theoretical amount is just going to be the maximum. You know you could never get any more than this. That's all it tells us. And then your products, one of the things that might happen is if you have a reaction where more than one thing, for instance, maybe is precipitating, well, then then what I have is actually a mixture of two things. It's not pure. And that's going to mess up your results. So there are other factors you have to deal with when but this is just saying, well, if in a perfect world, this is what would happen. And we don't live in a perfect world. I don't even know if I don't think that's necessarily part of the curse. It's just part of the way God made his creation work. I don't think it's part of the curse at all. It just is what it is. Okay, so you have to have a balanced equation. They either have to give it to you, which at first they probably will, and then as time goes along, they will expect you to do more and more of it yourself. But this is only going to be under ideal conditions. So the first one we said we were going to do is moles to moles. So we're starting out moles of known to moles of unknown. Now maybe one thing I should say is the moles of known doesn't automatically mean it has to be a reactant. And the moles of unknown doesn't automatically have to be a product. It could be the other way around. That's the way you're going to do your lab. Your known is going to be the 2 grams you want to make. And then you figure out what's the unknown. What do I have to mix together to make that? So it could be that way. Your known could be your product. It could be your reactant. It just kind of depends how the problem's been asked. Okay? So as Laura had for her answer, what do we use mole ratios for? Conversion factor. Okay? Here it actually says that. This plan requires 1 conversion factor, and that's my mole ratio. And of the unknown substance to the known substance or given, your book uses a lot of the word given. I use the word known. And the mole ratio is always set up like this. Your unknown coefficient's on the top. Your known coefficient is on the bottom. Okay, make sense? Okay, so you're going to write your given quantity, and as I told you, I think starting way back in physical science, you want to always write your given in chemistry. Well, actually in physical science the same way. You always wanted to write it over 1, because we're going to use a conversion factor, and conversion factors are always fractions. So let's write the beginning thing as a fraction. So you're just thinking fractions. So you're going to write your given, you're going to multiply it by your conversion factor, you're going to get your unknown. So in a more colorful fashion than what's up there, because our printer can't print color, that's basically what's up there, or what you have on your sheet in front of you. So you have, this is the whole thing that you have up there. What we're talking about now is just moles to moles. It's just that middle part. It's like you're standing on the banks of the Missouri River on Omaha side, and you want to end up on the banks of the Missouri River on the Council Bluffs side. The only thing in between you is the bridge. Okay? And that's the mole ratio is your bridge, which you get from a balanced equation. Okay? So let's do some problems with these as we go along. It says in a spacecraft, the carbon dioxide exhaled by the astronauts can be removed by its reaction with lithium hydroxide according to the following chemical equation. Now, if you have watched the movie Apollo 13, on their way back, they were having trouble with carbon dioxide buildup because because of the damage that had been done to the let's see which part what module was that called? The part with the oxygen tank in it and stuff like that. It's kind of like the supply module portion of it. And so they had to come up with a way, and they just went into the lunar lander, which they never were able to use because the damage that they had. They went in there, jerked out they call it a CO2 scrubber is what they call it. But it does what it says here in that it takes the carbon dioxide you've exhaled and reacts it with lithium hydroxide. And it's, in other words, it's taking carbon dioxide out of the air and then just leaving it air normal. And so they took that out of there, and we use the word jerry-rigged it, but they made it so that they could hook it up to their other system with duct tape. I don't know where they had it. I guess that was one of the things they have along. Duct tape is a great thing to have with you. They didn't have duct tape in olden days, my dad said, and so they used, everything could be fixed with baling wire. There's the wire that they wrapped around a bale of hay, but everything could be fixed with baling wire. And my dad thought so much of it that he gave me kind of like a spool of baling wire. When he was still preaching, he'd have to do odd jobs on the side, and one of them is he'd care for people's cattle when they were on vacation or something like that. And he'd have to take the wires off the bales, and he'd save all these wires, and he'd wrap them up. And I still have part of that spool of baling wire that he wound up probably 30 years ago, probably. I still keep using off of it. It's the thing I like about baling wire. It has a certain amount of stiffness, but you can always straighten it. You can always make it nice and straight again. It's stiff, but you can still straighten it. Some wires, once you got it bent, it has this kink in it, and it's hard to get out. But not that. So it's good stuff. So they use duct tape, though. I mean, I suppose if they'd had some rolls of wire up there, they could have wired it together somehow, I guess. One wire that does work kind of nice, it's a little stiff side, is if you have these metal clothes hangers. People will use that. So here is our chemical formula, carbon dioxide plus lithium hydroxide. Lithium hydroxide is actually a solid, as they're using it here. And the carbon dioxide will react with the lithium hydroxide, and it's going to form lithium carbonate. Lithium carbonate. And then water. So in other words, water is a byproduct of this reaction. And they want to know how many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide, that the average amount exhaled by a person each day. Now, if you're an athlete, you exhale a whole lot more than that. Okay, but this would be just the average person with, maybe working at a not so strenuous job, I guess. Maybe, let's say you have an office job. Maybe that's more like this. 20 moles, we're going to get rid of that. So they want to know how many moles of lithium hydroxide do we need to be able to react with those 20 moles. Okay, so here is our formula. Is it balanced? Do they say it's not balanced? First of all, they don't say it's not balanced. And the other thing that I would suspect that it is balanced, there is one coefficient there. Now, if there were no coefficients, I would be suspicious that maybe it's not balanced. It might be, without having to add any coefficients. But I see a 2 in front of the LiOH, so it's probably balanced. So what I do is I'm going to write down my given 20 moles CO2 over 1. 20 moles CO2 over 1. Then I'm going to multiply it by my conversion factor. And my conversion factor is going to be between CO2 and LiOH. But remember, my known has to be on the bottom. And that was carbon dioxide. So the CO2 will be on the bottom. My LiOH is going to be on the top. So I even want my formulas to cancel out. I want my formulas to cancel out. So Here's just listing your givens, your unknowns. Okay, let's actually solve this thing. So there's my 20 moles of carbon dioxide over 1, and then there's my conversion factor. Notice that I have my CO2 on the bottom and my LiOH on the top. And I just look at what are the coefficients in front of it. Here it still writes the moles, but you don't have to write the moles over moles. The 2 is in front of LiOH. The 1 is in front of CO2. So it's 2 times 20 divided by 1. And that just shows you everything canceling out. My moles cancel out, my CO2s cancel out, and my answer is 40 moles of LiOH. So I need 40 moles to be able to use up all the CO2. You got that? Okay, so any questions? Okay, so let's do another one. Only this time, let's start with moles of a substance, known as in moles, but we want to find out how many grams of something do I need. So that's going to be my unknown. And on my stoichiometric problem solution guide, it says I'm starting out with moles. Okay, I'm right next to the bridge, and I want to end up with grams of unknown. So I have 2 conversion factors, a mole ratio and a molar mass of my unknown. So I have to do a molar mass on this one. So you're going to use 2 conversion factors, a mole ratio and your molar mass. But it's a molar mass of the unknown, not the known. So be careful on that. So that's why the guide, you see this mole ratio over here, it's on the unknown side. So you'll know which mole ratio, a molar mass to make. If you figure out the wrong molar mass, it's not going to help you. Also, it wouldn't count out. If you're writing all your units, they wouldn't cancel out and you know you did something wrong. Okay, so if I look at my guide, only in colored version of it, and I have moles, I said I'm starting here next to the bridge, and I want to end up here in eastern Council Bluffs. Moles to mass. Okay, so here's our problem. In photosynthesis, plants use energy from the sun to produce glucose. We studied that last year in biology. And oxygen is also one of the products. In addition to that, what is the mass in grams of glucose that's produced when 3 moles of water react with carbon dioxide? Now, they're not talking about how that takes place. It's just that this is going to be the reaction. And so I have to list what's given. Well, I've been given 3 moles of water. 3 moles of water. And then what's my unknown? They want to know how many grams of glucose are going to be produced. How many grams of glucose? Now, they don't tell us anymore. They don't even give us a balanced equation. So we need to write that. So, you know from last year that what 2 things react to make, or what are the 2 things you need besides sunlight and chlorophyll do you need to make glucose in photosynthesis? What are the 2 things you need? Need to have, kind of implies one of them right here is what? Water. And the other one is what? Carbon dioxide, okay? So to write your equations, write down H2O plus CO2. One thing that I would remind you, or not remind you, but maybe tell you, when you're writing these formulas, you have a formula, then you have a plus sign, and then you write the next formula. Leave enough room between that plus sign and the next formula so you have a place to write your coefficients, It's so easy to just write it like that, all packed together, and then I have to somehow squeeze in a coefficient in there. Okay, and then I have an arrow, and then what's going to be my products? It tells you here what the products are. What are they? What are the products? Does Mr. Ben know what it is? What are the products? No, that doesn't work in here. What are the products? Well, it's up there on the board.
Carbon dioxide.
Well, that's one of the reactants.
Oxygen.
Yep, oxygen's one of them. O2 is one of them. What's the other one? What's kind of like the main goal of photosynthesis? To make what? Glucose, there you go. Okay, and the formula, they gave it to you. You don't have to remember this one from last year in biology. C6H12O6. Some of you probably still remembered it, but okay, so that's what's being produced. Okay, so here's my version of it. I have glucose in front of oxygen, but it doesn't matter, remember? Okay, so there's my unbalanced equation. Now, it also has the other little letters in it that indicate, what physical states it will be. Carbon dioxide, we know, is going to be a gas. Water's going to be a liquid. Glucose is going to be a solid. It's like sugar. And oxygen's obviously going to be a gas. Okay, so it's unbalanced. Okay, so we need to balance this. What do we need to do? What we need to get this thing balanced? How many carbons do I have on the left side? One. How many carbons on the right side? 6. So what am I going to have to do with the left side? I'm going to have to put a 6 in front of the CO2. Okay, so I put a 6 in front of the CO2. You could go with oxygen next or hydrogen. I think on this one probably, notice you on the right side you have oxygen by itself. And when we were learning how to balance equations, we said if you have an element that's all by itself, leave it for last. So let's leave oxygen for last. Let's do hydrogen. How many hydrogens on the right side? How many hydrogens on the right side? 12. So what do I need to do with water that has hydrogen on the left side to get 12? What would you do?
Yeah, 6.
I'd put a 6 there, right? I'd put a 6 in front of H2O. Okay, now we're down to oxygen, so we're going to have to deal with that now. How many oxygens on the left side?
Are you talking like without the coefficients or with the coefficients?
No, all total right now, as it stands.
There's 18.
18? Okay, have 18. With the mask on, I always have to kind of imagine what people are saying. 18, I'm just giving you, sometimes I've done that and somebody, yeah, that's okay. I didn't imagine them correctly. They gave the wrong answer, but I just imagined them saying the right one. Okay, so 18 on the left. How many oxygens are in glucose? There's 6. So I need to have 12 more, right? So I need oxygen to supply the other 12. So I'm going to need to have what in front of oxygen? To get 12 more oxygens.
I'm going to go 6.
Yeah, I'm going to go with 6 too. You notice they're all 6s? Except glucose doesn't need one, does it? That's where we have to. So that's our balanced equation. Now I can do mole ratios and stuff like that. So we're going to write down what's given, and that was 3 moles of water is going to be the first thing that we're going to write down. And then if I look at my problem solution guide, the next thing going across here is my mole ratio. So I'm going to write my known on the bottom. So what compound goes on the bottom? Water goes on the bottom. H2O will be on the bottom of my mole ratio. What's going to be on the top? Our unknown is what? Glucose, right? C6H12O6. That'll be on the top. And what coefficient is in front of glucose? Mr. Will, what coefficient is in front of glucose? What does it look? Do you see one in front of it? So that means then must be what? 1. Yeah, just like in X, 1X and X are the same thing. So there's 1 there. So I'm going to have a 1 on the top with the glucose. And on the bottom, I'm going to have a what? What does Brianna say? On the bottom, we're going to have is water. So what's the one in front of water? No, what number's in front of water?
2, 1.
Right? I wish I could point at it, but I can't. 6. There we go. That's what we want. We want to have a 6 there. 1 mole over 6 moles. Or 1 C6H12O6 over 6 H2Os. Okay, that's my conversion factor. Am I there yet? No, because we need to go all the way over here to mass. So we're going to have mole ratio. Next, mole ratio of what? Not mole ratio, wrong word. Molar mass of what? It's the molar mass of my unknown. What was my unknown? Glucose. So I have to figure out the molar mass of glucose. 6 carbons plus 12 hydrogens plus 6 oxygens. Okay. Each carbon is around 12. I think it's 12.01 or something like that. So 12 times 6 is what, 72? Each hydrogen's about 1, so there's 12 of those, so 12 more. So 72 and 12 is 84. And 6 oxygens, each one's 16. 16 times 6 is 96. Now, whatever that adds up to, we were at 84 plus 92, is that not 92? 96. So there's the actual answer is 180.18 grams of glucose. Now, why did I put it on the top, not on the bottom?
Because you needed the one mole of glucose to cross out with the other one.
Yeah, we want this 1 mole over here to cross out with that 1 mole over there. We want the moles to cancel out, so I need to have the gram on the top. My waters will cancel out. 2 of the glucoses will cancel out, but it'll still leave 1 on the top. And then when I multiply all those together, 3 times 180.18 divided by 6, I am going to end up with 90.1 grams of glucose. 90.1 grams of glucose. So, anything about what we've done so far that doesn't make sense? Okay. So it's kind of just, if you could have the guide to tell you what the next step is, and you know how to do molar mass, you know how to balance an equation, so you can get a mole ratio, you know, it's just math, you know. Let's see. Let's just stop right there. We'll do the other 2 I guess we got as far as we're supposed to anyway. Well, almost. Yeah. Had wanted to do a demonstration today. I've got part of it, and I thought I had all of it, but I don't. I need to have pure isopropyl alcohol. You know, the isopropyl alcohol we have at home is always mixed with water. It's, I think, like 70% isopropyl alcohol and 30% water. It needs to be pure to do this demonstration. So I went to Menards thinking maybe they might carry pure isopropyl alcohol, but not. I'm thinking, where else could I look? Maybe at a pharmacy? I know you can get regular isopropyl, what they call it, yeah, like rubbing alcohol, but so I have to figure out where I can get that. It's a fun demonstration. You'll enjoy it, but yeah, the purer they are, the more expensive they are. That's true. Yeah, the purer they are. In fact, when I order chemicals, they have different grades. They have some that are called a reagent grade. That's the highest one. And then they have student grade, like we do in a lab.